Assalamualaikum and a very good morning to all of you. So for today I would like to describe about my experiment, which is experiment 4, which is experiments the Ionic transport number, the studies of Ionic transport number by moving bonding methods. First of all, my name is Nick, and for today I would like to briefly explain to you about this experiment. I've been working this experiment with my partner Faris Izwan. We both from a Bachelor of Science in Pure Chemistry, and yeah, throughout the experiment we have been supervised by our supervisor, Dr. Yin Yin Kyo, and all of us from departments of chemistry, Faculty of Science, University of Malaya, and this experiment fall under the course of SIC 2004 Physical Chemistry 2. And yeah, and now we're moving on into the introduction of this experiment. So there are a few terms that I would like to introduce, which is the first one, that the law that I keep mentioning throughout the experiments, has been founded by this one German physicist, and this is the law, which is the Clorox law, and this is the founder. And his name, as you might wondering, who is he actually? And he is Friedrich Clorox. He was a German physicist, and he was born in 1840 and died in 1910. This German physicist came up with a great idea about the molar conductivity, and from this law we can truly explain about the whole agenda, the theory and stuff. Okay, and then as we moving on into deeply into the laws of Clorox, because we've been using this a lot, and I will explain to you a lot about this law. And by the law is this law really mentions about the molar conductivity. The law states that by having an electrolyte, this electrolyte will then having equivalent conductivity, which at infinite dilution, that is equal to the sum of the conductance of anion and cation. So by mathematically equation, we can simply say that molar conductivity is equal to the sums of the molar conductivities of cation plus with the anion. So for example, okay, let me show you an example here. As we have the electrolyte here, we have NaCl solution. So Na solution then will dissociated into Na plus Cl minus. So then by mathematical equation we know that the what we call as the molar conductivities of the electrolyte is equal to the sum of the molar conductivities of the Na plus with the molar conductivity of the Cl minus. That is what truly means by that mathematical equation. And then by simply knowing that from the law, we know that we can relate with the migrations of the ions at the migration of the ion, that each of the ions migrate independently of its co-ion at infinite dilution. So what is meant by this? Basically, if you have the solutions, simply for example Na plus and then Na plus Cl minus, as we know that Na plus is basically let's say we're considering Na plus as our determinations of ion. So the co-ion will be Cl minus. So this law mentions about the migration, independently migration. So Na plus then will move independently to the respective electrode, same as the Cl minus also will then move into its preferred electrode, that what mentioned by the second statement here. And then we moving on into this other slide. Okay, and this as we know by knowing the conceptual of the Clorox law about the molar conductivity, we can actually relate with this one terms called migration of the movement of the ions, isn't it? So simply, this brilliant physicist came up with a great idea to relate the ideas of regarding motions of the ion to the molar conductivity. Okay, and then as we moving further to the movements of the ion, okay, if there are movements of the ions, it will then result in the conductivities of an electrolytic solutions. let's say we have the system, electrolytic system, then the migration of the ions will then go into the appropriate electrodes. This migration will then result in the conductivity. That is what means by that. So that is what the relationship between molar conductivity and the movements. So the motions of the ion, by considering these experiments, we call as a thermally induced random motion or Brownian motions, whereby the process called diffusion. Diffusion basically happens specifically when there are externally applied electrostatic field called electrical current. So for example, let's say we have the solution here, and then we have electrode. This is only for example here, and then we have been supplied by electrical current here. I noted as EC. EC is electrical current. And then let's say we have the anode here, and then we also have cathode here. Okay, and then what happened is that the migration of the ion is followed the electrical current direction. Let's say electrical current will then move from, so let's say this one is positive and this one is negative, then we'll move into anode into the cathode, isn't it? So then what will happen is the ion also move into the respective appropriate electrodes. Let's say ion Cl minus, for example, then move into will move into anode, and then Na plus then will move into cathode. That's what means by that movements of the electrode by relating into the electrical current. Okay, so as for example, as I mentioned, independence of ionic migration, this mobility of the let's say we have NaCl solution, isn't it? NaCl and then Na plus Cl minus. Okay, and then the moments of this Na plus is not going to be affected by the Cl minus. Cl minus only accompanying ions here. So both of the ions will then move independently. Okay, so by doing the experiment, I will briefly explain to you more into independence or ionic migration. Okay, and then back to the slide. And then lastly will be the relations of the molar conductivity and the concentration. So by seeing this graph, actually the molar conductivities can be actually be related with the concentration. By definition, electrolyte is the substance that contains free ions. So electrolyte is basically can conduct electrical, as they are a free moving ion inside the system. So the strength of this electrolyte is depends on the concentration, so the amount of the ion present. So let's say we have strong electrolyte. Therefore, strong electrolyte we have many ions, while the weak one having few ions, okay, present. So by considering the strength is really can describe how good the conductor is. Let's say a strong electrolyte is a very good conductors of electricity, while the weak electrolyte are the weak conductors of electricity, and non-electrolyte cannot conduct electricity at all. So by this graph here, it mentions that some sort of relation between molar conductivity against the square root of concentration. As you know, by seeing the graph, that molar conductivity actually increases with the concentration of the electrolyte. So this one, please note that this graph is basically molar conductivity against the square roots of the concentration. It will not affect. You might see decreasing, but then it will increase. So by the following term, I will describe you later. And then I would like to show you more into this relation, what we call it, molar conductivity. I donated as a molar C, and also the concentration. As you can notice in the very first slide, I mentioned about infinite dilution. What actually means by that? So molar conductivity is what we call as a concentration dependent. Okay, So it's basically a concentration dependence. Hence, when the concentration drop, the change in the conductivity begin to approximate a linear dependence upon concentration. So what is meant by that? So let's say we have a graph, we have the molar conductivity against the concentration. So what will happen is you will see that there are increasing of the concentration for the weak electrolyte. You can see a very straight linear, but for the this one is for the weak, pardon my handwriting. For the strong, you will see a very non-linear, the non-linear graph happen. So to summarize, molar conductivity increase with the dilutions. This concentration is that in the form of dilutions lah. So therefore, by plotting the graph, conductance versus concentration, conductivity versus concentration, basically it is possible to extrapolate the date to obtain the values known as molar conductivity at infinite dilution. As to be concluded, as we notice that the concentrations of as we know that the concentration on its infinite dilution, it will exhibit molar conductivity near to the actual molar conductivity. That's why we always refer to the near the infinite dilution. Because of that molar conductivity is near the actual one. Okay, and then we go for the next slide, and yeah, as previous discussion, we already discussed about the movements and that can relate in to the conductivity. Hence, there is new terms that need to be related, which is electrical mobility per unit electric field. As you can see here, in principle, what can I say? The movements of ion is related to the molar conductivity, and the movements of the ion is occurred in thermally induced motion called diffusion. Therefore, as a result, as the electric field applied, the ions start to migrate. It will then influence the molar conductivity. As we fulfill the definitions of electrical mobility, in principle, electrical mobility is described by how the ability for a charged particle to move through a medium which respond to the electric field that pulling them. As I show you just now, we have considering an A plus solutions, then how the anion and cation move into the respective electrode, isn't it? Right? So yeah, and then therefore by definition, mathematic equation, we can simply say that limiting molar conductivity is equal to the ionic transport number times molar conductivity over ion number. As you can see here, there are two terms, new two terms have been introduced. The first one will be limiting ionic conductivity, and then ionic transport number. Limiting molar ionic conductivity is a term that to describe the conductivity of the solution at very infinite dilution. By example, all the ions have dissociated. The ions are farther apart. Therefore, limiting molar conductivity will increase with the decreasing of the concentration. That is what I tried to mention from the previous discussion. So, we mentioned about the molar conductivity and the what we call as a concentration. So both have been related, isn't it? And then second term will be ionic transport number. So this term basically have been introduced by Hitruth in 1853, which can be defined as the fractions of the total electrical current carried in an electrolyte by given ionic species. And then differences in transport number arise from differences in electrical mobility. Ionic transport number is used to basically identify the moments of the ion inside the electrolyte system, if we consider an electrolyte system. Okay, and then we go for the derivation. As you might wondering, what is the actual relation between ionic transport number and also the electrical mobility, isn't it? So basically, as you might wondering, here is a derivation, but I will not explain much about this. This is just to show up to you as there are derivations of equation happen. At the end, you can see that t is much related to the speeds, which denoted as u plus and u minus. the signage indicate the types of the ion, cation or maybe the anion. Okay, so the one that I circle in this slide is the one that the result that we use. At the end of the day, we don't simply use all the derivation. That's all physicists do. But we chemists, we only investigate the equation, the end of the result, the result of the equation. And then we're moving forward to the method. We have two methods: heat trough and moving body method. So heat trough is basically have been created, have been founded by Johann Wilhelm Hittorf in 1853. He was a founder, and by studying the electrolytic cell, the concentration is reduced at the electrode. So differ from the moving body method. He was actually discussed, founded by two British physicists named William Cecil Dampier. He started the research by 1896 and continued the research by Oliver Lodge in 1893. Okay, a simple introduction. I will go into the basic principles of the moving boundary method. Moving boundary method is all about the boundary that can be seen, a visible boundary to be exact. As throughout the experiment, you will see that there is a visible boundary that can be noticed. And there are a few principles that we use in this method. The first principle that we use is the movements of the boundary between two adjacent electrolyte. And basically this two electrolyte is influenced by electric field. Okay, the second principle that we use is composing by this cell composed of leading and indicator solutions. Leading solution would be the one that what we call as the indicator, the one that we wanted to investigate. The indicator will be the one that indicate the movements. Okay, the selection of this solution, these two solutions are very important, as it will influence the movements of the cation and affect the transport number. Fourth, the movements or the moving body method kindly used to exactly determine the ionic transport number. This is one of the methods. Okay, by moving body method, the observable boundaries between solutions can be seen. The selection of the indicators electrolyte is done carefully to ensure the movements of the cation is slower compared to the cation, as we stated in the third principle. Okay, whose the transport number is to be determined. In this experiment, we considered hydrochloric acid and also HCl plus and Cl minus ion present in HCl has to be determined. So HCl mentioned about this principle of the electrolyte. This is crucial to maintain the boundary that is formed. So basically what we can observe from this experiment, so the distance between the boundary is basically that we investigated. The distance traveled by the boundary is directly proportional to the cationic and anionic velocity, respectively to the equation that we show from the derivations of the moving boundary method. And then now I will show you the schematics of the moving boundary method. This is a what we call as a diagram that you can see in the screen now. You can see the indicator and also the leading solution. So in this experiment, we will use more into lithium chloride solution and also the hydrogen chloride solution. So, and we will use platinum electrode and also the what we call a silver chloride solution. And then we have been applied the electrical current to the system, so that we wanted to really what we call as we wanted to make the presence of the electrical current so that the diffusion will occur. Okay, and then we're moving on into the other slide, which is the objective. Basically, this experiment focus on the studies mainly about the determinations of the ionic transport number of H plus ion in the aqueous solutions of mainly that we use is 0.1 molar HCl at given temperatures of 31 degrees Celsius. So for the methodology, I simply say that there are 4, but then I try to mention here there is only 3 that we do. So the first one will be installments of the leading compartment. The second one will be installments of the indicator compartment, and the third one will be running the compartment. So the part one will be the installments of the leading solution. So as you can read in the screen now, what we do is basically we wash the leading compartment using HCl to ensure that all the unreacted substance wash away from the experiment. This is to ensure that there is no what we call as wastage in the compartment, and also we try to wash it with the chromic acid, as we know that chromic acid is really functional to to clear away all the stuff inside the compartment. And then as you go to the, and then we attach with the silver chloride, we fill up with the HCl and stuff. And not to forget, we put some indicators to show the color, because our HCl is colorless. And the second one, sorry for that. And then the second part will be installments of the indicator compartment. And sorry for that. And then we try to remove the HCl from the top using the dropper, as we try to fill the first compartment fill it with the HCl, and then we try to remove some from the top of the compartment, and we wash with the anode cell several times, and then fill up with the lithium chloride solution, and then slowly we attach the platinum electrode. And then there is some white powder that we use to in the indicator compartment, which is the lithium carbonate powder. This simply to increase more the concentrations of the lithium. And then part 3 will be running the compartment. We supply the electric current, and the current need to be maintained like 3 milliampere across the experiment, that because we really wanted to let this kind of variable to be constant. We don't want that kind of thermally infused movement or the Brownian motion happens. Okay, and then the time is recorded for the boundary to reach graduated tube. And as you can see in the screen, this is the setup for the experiments, and then you can see the observation here. So basically from this observation you can see the exactly the boundary is moving downwards. It follows the current's directions. So it's by principle we know that actually is fulfill the definitions of the electrical mobilities per unit electric field. And then as we moving on into the result, okay, this is the graph that I get. Basically we plotted volumes of boundaries against the time, and then you can see the what we call as a and sorry, we can simply say that we have a linear graph here, volume versus time. And then for that we do the simply regression of the data, and this is the data that I do regressions, and from that I can extract the values of intercept, and also the what we call as to get this kind of uncertainty of the data for the treatments of the data. And then okay, interpretation of the data, basically from the graph we know the gradient, and then from the regression we know the lower boundary and upper boundary, so that we can actually get the uncertainty. And then this is the gradient that we get, 0.114 plus minus 0.0001 centimeter cube per second. This gradient actually shows what we call as the speeds of the boundary. So the boundary travel in the time, so we can actually investigate from that boundary. Actually we can extract the information of the Ionic transport number, and then from the boundary we can do the calculations about that, and then basically we get 0.367 for this Ionic transport number. And then for the treatments of the data, and then we calculate the uncertainties of the gradients here to show you how to really calculate the uncertainty. And then we get like 0.00124427. And then for the Ionic transport number we calculate, and then we get 0.006 for the uncertainty. And then and then we're moving on into the discussion. There are two main points I would like to discuss here. The first one should be Heathrow rules, and the second will be qualitative tests. So Heathrow rules basically explain the reductions or the concentrations of the LICL near the Ag and AgCl electrode. So across the experiment, what my supervisor say that you can see there is some sort of reductions in concentrations of lithium chloride near the electrodes. So from that we can conclude that, simply say that is by applying Heathrow rules, therefore the migrations of the ion really can happen. That's showing that the movements of the ion really happen throughout the experiments, and the lithium ion really migrate from another side to another side. And then discussion should be another part, which is qualitative tests. Qualitative tests should be in the part 4, but due to the Heathrow rules and the reductions of the concentration of LICL, we do not do this part 4. But what I'm trying to do here, I will try to explain theoretically what happens to the movements of the boundary. And this is the Heathrow rules. Basically, I would like to simply define it for you. And basically, there's a observation near the electrodes of the platinum. The colors of the solution that we propose to be blue for the lithium chloride solution, but then it's turned out pale over time, as we know that they are decreasing of the concentration near the PT cathode. Okay, and and we propose that what can simply be told is just that maybe because of the migration of the ion happens. So you can simply say, by mentioning Heathrow rules, the relation between the speeds of the movements of the ion is directly proportional to what we call as a loss of the concentration near the electrodes. And then as we move further into the further discussions, we do run the compartment like 1 hour. So we notice that as we go what we call as we go over time, the movements of the boundary is slower and slower and slower. So this kind of explain the migration of the ion more, because of most of the ions is being used throughout the experiments, and we cannot see that, we cannot explain that we can explain that why the time for the boundary to travel is lower, because more ion is being used, no more ion is going to be in the process of the diffusion anymore. And then as the amount of the surrounding electrode is less, by knowing this, I make an assumption, which is saying that there are not enough ion inside the cell to help the migration. Okay, and this is the qualitative test, which is I theoretically explain. As we shut off the current, what happened is that sorry for the noise when it is short. Okay, so what can be observed is just sorry for the noise again. And what can be observed is basically the boundary goes up. The motion of the ion is observed immediately. This mobility of the ion is said to be influenced by the applied potential. The transference numbers of H plus ion is determined to show the motions of the ion is occurred during the during the electrolysis cell, and ion and cation are carried by the current. So the amounts are carried by each directly proportional to its speed. So you can see the movements. And next we do switch off the current. The levels of the boundary went up slowly, and the colors of the boundary become slightly unclear. This is simply because of the motion of the ions of the diffusion. We cause the boundary to smudge, to become sharp and clear. It is happening at the same, at the early time of this migration. You can see that leverage of the what we call as let me show you. You can see that as the bonding goes down, as the bonding go down, then you can see that there is leverage here happen. So, and then over time it will turns into more straight line here, like this. Okay, and this is the early observations of these boundaries, and then it become like kind of uh, straight line over the boundary. So, yep, and we're moving on into the next slide. And when we switch on the current, the levels of the boundary went down again as the current is fluid, and then you know that it will, affected by the electrical mobility. And then when the current switch on, then the level boundary went down again, and the color become clear because it shows that the movements of the ion is there. So, and then this is simply because of the ions of the H plus and uh, lithium ion from the LiCl and HCl will detain by difference in the field potential between both of the liquid. So, yep. And then qualitative test also indicate electrical conductions of the HCl over is greater than electrical currents of the conductions of LiCl. What I try to say is that this is more into the size matters. When you have like smaller size, then it will move like faster compared to the Li having like um, bigger size compared to HCl. So yeah, as you can see here, the less difference of slope potential between HCl and LiCl will appear. So as a result, ion H plus will then remove faster because of the strong electric field, isn't it? So that HCl will then enter again, and then the slope, the existed slope potential Li plus will detain between diffuser into the HCl. And then next we do reverse the conducting electric current. So the levels of the boundary can be observed to kind of went up slowly but faster when no electric current pass through. This is simply because of the ion H plus and Li plus remove conversely. So then exchange of the electrode will cause the electrode platinum become cathode and electrode argentum become the anode, the switch of the electrodes. So if you have like before this, we do let the PT to be the anode and then silver chloride to be the cathode. When we switch off, there will be in what we call as the movements of the ion will like change direction because of it follows the electrical current compared to the compared to what happened just now. It's just like how you change the current direction, it will then influence the electrical mobilities of the ion. That's what I tried to mention in the early introduction, isn't it? And then ion H plus and Li plus will then remove faster because of the different potential between two liquids. The boundary then will go up because of ion H plus will then having a smaller size compared to the lithium ion. This is more into the what we call it the size matters, is what I said in the previous slide. So apart from that, we've been given questions, as you can see in the screen now. So this is the question that we got. So from this mathematically equation, we do calculation and stuff, we do notice that the factor that affect the limiting molar conductivity will be the size of the ions. And yeah, we simply say that size and ion mobility is related by simply say that the limiting molar conductivities of the H plus ion and Cl minus values are too different because of the conductivities of ion also depends on the size. Then we know in this case H plus is smaller than chlorine ion, so as a result ion H plus having greater mobility compared to the Cl minus. And then for the Cl minus, it has a bigger size compared to the water molecules, because water molecules cannot be dissociated, and then it will then surround the Cl minus This is, if I'm not mistaken, the caging effect. This will then reduce the potential and motions of the ion Cl minus. That's why you can see that the motion of the Cl, the motion of the chloride ion is very slow. And then we try to investigate more into the non-common ion compared to the common ion, which is the Cl minus that we use across the experiment. And then that's why we simply say that limiting molar conductivity for H plus ion values is larger than compared to the Cl value. And then for the conclusion, the ionic transport numbers of H plus in aqueous solution is 0.1022 molar HCl at given temperatures of 31.0. So this is the reference that I use. Thank you and have a nice day.